Okay, this is meant to be a tutorial for people who aren't super familiar with Gaussian processes. And just check that this isn't completely misguided. Who already knows the Gaussian process basics? Hands up. Okay. Who doesn't know the Gaussian process basics? Okay, good. So apologies to the huge majority. I think it's a good idea that we have a talk aimed at those people so they can get up to speed and know what everyone else is on about. Okay? And you guys who don't know the basics, it's your job to, since this is for you, don't say, okay, I'm not understanding, I'm going to go to sleep, it's for you, and so interrupt especially. And if anyone else realizes that I say something that wasn't clear and you think you can understand, go ahead and interrupt and join in. Okay? Great. So, people who don't know Gaussian processes basics, do you already know about neural networks? Is nonlinear regression with neural networks a familiar thing? Hands up if it is. Okay, a little bit. So we can use that language to make connections and clarify things occasionally, maybe? Okay. And how about Bayesian complexity control for neural networks and automatic relevance determination? Are those ideas familiar to those people as well? No. Okay. Great. All right. References. The Bible of Gaussian processes is this thing you'll probably be hearing about. It is Rasmussen and Williams on the right. In my book, in chapter 45, there's Gaussian processes stuff as well. And it's much shorter, obviously, than the Bible. But mine in the index does have an entry on Bletchley Park. So those of you who are already trying out your wireless connections, you can download the book and enjoy reading about Bletchley Park. And the notation I'll use will pretty much match the Rasmussen and Williams notation. They asked me to, so I tried hard to match their notation. Okay, what are we doing with Gaussian processes? The aim is to do the sort of things that people do in machine learning with feed-forward neural networks. You have a data set of input-output pairs, and you're trying to predict the output as the input, and you can think of this as non-linear, high-dimensional curve fitting through the data. So the x's are the horizontal coordinates of some data point, and the y's give us some vertical coordinates, and we're trying to come up with some non-linear curve that goes through this high-dimensional data set. So, the question is, can we achieve these interesting, non-trivial problems of things like classifying phonemes, classifying text in terms of pronunciation, handwriting recognition, and so on, all these machine learning tasks? Can we actually solve these tasks with the boring old Gaussian distribution, which is just defined by a very simple formula here? K will always be the name for the covariance matrix of a Gaussian distribution. So this is a zero-mean Gaussian distribution. The covariance matrix appears inverted upstairs in here in this quadratic form, and this is finding a probability density over y1 and y2. And here's a contour plot of an example probability distribution. So can we do interesting machine learning problems just with Gaussian distributions? That's what Gaussian processes are actually about. So let's start by reminding ourselves how two-dimensional Gaussians work. And I'm going to show you a whole load of pictures in which I'll try and keep the color code fairly consistent. So when I'm going to draw points from the prior, those will be shown in blue. So let's start by doing that, and maybe I need to have the curtains closed. Okay, so the covariance matrix I chose is shown here. It's 1.8 something, 0.8 something 1. There's the contour plot on it, and I'm going to draw some points from this probability distribution. There they are shown in blue. Great. Okay, so we can draw points from Gaussian distributions. Now, one thing you might do with the Gaussian is you might learn the value of y1 and then ask, now that I know y1, what is y2? So let's say we learn y1 and we find out that it's equal to 1. So now the answer to the question, what do we think y2 is well, if these blue lines, if these blue dots, if some of those had actually fallen on this red line, the probability distribution of those samples is what we wanted. Now, none of them did actually fall on there. but we can easily compute or visually just fill in what now the probability distribution of y2 is given y1. Okay, and it's shown by this green thing with error bars. Okay, so before we knew y1, y2 could have been anything in here, but now that we've seen this particular value y1, the mean and the standard deviation have changed a little bit. Okay. Another way we can render this posterior distribution of y2 given y1 is we can draw samples from it, and those are shown in light blue here. Okay, we can play this game again with a different covariance matrix. So I'm going to switch now to the second covariance matrix on the left-hand side, this one, which has less strong correlation between y1 and y2, and here's its contour block. Okay, same game. We're now going to draw some samples from the prior in dark blue. Then we're going to imagine that we learn the value of y1, and now we say, what's our inference about y2? And what I'd like you to notice is our inference, now they're less strongly correlated with each other. Our inference has bigger error bars, and the mean, although it's not 0, is not as far away from 0 as it was last time. Okay? So this is just pictures showing you Gaussians. Okay, there's some samples from that posterior distribution. Now let's move on to the third one with strong correlations. That's what the contour plot of the strongly correlated Gaussian looks like. There's some samples from that distribution. Now imagine we observe y1 and it's equal to 1. What's the posterior distribution of y2? Now it's a very tight distribution there, shown in green, and here's some samples from that distribution. Okay, so this is all simple, ordinary Gaussians shown in pictures. The mathematics of what's going on behind the scenes is on the next slide. So what I've been showing pictorially is our predictions, the posterior on the unmeasured variable, conditional on the y1 we measured. It's a Gaussian. It's a new Gaussian with a mean that depends in some way on what we measured. And here's the actual formula. Don't bother with the details of this. It's just matrix algebra. It's the idea. You write down the conditional distribution you want. That's proportional to the, well, it's defined to be the joint distribution divided by some sort of constant. We're interested in how this depends on y2, the thing we don't know. And so all we care about is how does the joint distribution depend on y2. So you faff around with matrices a bit, and you can munge this joint distribution, which was a Gaussian over y1 and y2, into a Gaussian over y2, which has got a mean and standard deviation that you can work out. It's just matrix algebra. Okay? And the only important thing to notice is that the mean is a linear function of the data that we put in. So in those pictures, the center of that green object was on a line. If we changed the y1 value, then the green thing would have moved linearly away from the origin. Okay, so I don't want to focus on equations because the Gaussian processes can be quite tricky, and it's not that the equations are tricky, it's the concepts that are tricky. Any questions up to now? Is everyone with me? Okay, great. What we're now going to do is we're going to change representation. Up till now, I was showing you points in a two-dimensional space. Here were the contours of the distribution, and here was one point, one sample from the Gaussian. And for no apparent reason, I'm going to introduce a new way of representing this point. This point is now going to be represented by a dot here with a height above this line y1, which was 1.2. So this is 1.2. And then another dot here, and that's at 0.9. Okay? So you can take any point in this plane and you can render it by two dots with a line joining them. Okay? Why are we doing this? Well, first let's just go through the familiar demonstration that we had a moment ago. I'm going to draw points from this Gaussian, but I'm going to show them in this new representation. Okay, so that point looks like this. And now I'm going to draw some points. I'll show them in sequence. Those are all points drawn from the Gaussian. Just like the blue points that were scattered over the left-hand side here. I showed them in a little movie. And here's a dozen of them. Okay? So this is the representation in this new way of looking at things of the blue points that were scattered over this whole bubble. Everyone happy? Okay, so now what does data look like in this representation? Well, data here was that we measured y1, but we didn't know y2. And in this representation, that red constraint corresponds to just a red dot here. So we now know y1, but we still don't know y2, so there's no red dot over here. So now we can represent our posterior distribution over what these line segmenty things are, like this. Okay, that is the posterior mean and standard deviation of y2. And we know that whatever y2 is doing, y1 is equal to this. I can show this again using samples from the posterior distribution in light blue, and I can show you a movie of samples from that posterior distribution. Okay? So all I've done is I've taken something you were already happy with and I'm showing it to you a different way. So why are we doing this? Well, the idea is that this representation of two-dimensional points can be extended to higher dimensions. This is a way in which I can visualize higher dimensional Gaussians. So what I'm now going to do is show you a six-dimensional Gaussian. So here's the covariance matrix that I've just pulled out of thin air, 6 by 6 numbers, and here is one point drawn from that six-dimensional Gaussian. So this is y1, y2, y3, y4, y5, y6, joined up by a line for no apparent reason. Okay, so what can we do? We can now draw samples from this Gaussian distribution that I've defined by picking out this 6 by 6 matrix. Here are a bunch of samples from that Gaussian distribution. And now we can introduce data, and we might, for example, have observed the value of y1, y2, and y6. So we've got these three constraints, and now the question is, given the Gaussian distribution, I'm assuming, what is the posterior distribution of y3, y4, and y5? And we can represent that posterior distribution, which is a three-dimensional distribution, in this same way of representing things. And it looks like this. This is showing the posterior distribution by its mean at each of those points and the error bars on each of those points. And I can also show this to you by making samples from that posterior distribution. These samples show not only the mean and standard deviations, but they also reveal the correlations between the predicted values of y3, y4, and y5. And I can show you a movie. So that's a movie of predictions about three variables that are part of a joint six-dimensional Gaussian distribution. And what I'm hoping might be happening for those of you who are new to Gaussian processes is I'm hoping that you might be getting a bit of an aha moment here. Because it looks a lot like nonlinear regression, right? So the question was, can we take a plain old Gaussian distribution and do nonlinear regression? Well, I haven't told you how this is working. I didn't tell you where this 6 by 6 matrix came from. But if you just look at this, 3 red dots and a green line with error bars, this looks a lot like nonlinear regression. Okay? So, I'm hoping you're having this aha moment, and I'd like you to have a chat to each other now to make sure everyone's awake. Okay? So, have a chat for 3 minutes or so, and we'll see if anyone's got any questions.
So what does
Ukraine, right?
okay,
I could also try to open the curtains at the very front. I don't know whether this is better.
Okay, so are there any questions about what I've shown you so far, especially from the people who this is aimed at? Are you... You're all very quiet. Come on, come on, come on. Any questions? Questions for anyone else? Are the people who I wanted to have an aha moment having an aha moment? Are we? Yeah? Yeah? No questions at all? Okay, come on. A question. Piotr, question. You had a question?
Well, I had a question how these movies were generated.
Yes.
meaning that these distributions, the samples you draw from this distribution didn't seem independent, one frame didn't seem independent from the next.
Dead right. Yep. So the samples aren't independent one frame from the next. If you pick any one sample out of the movie, it is a correct sample. But to make it look visually appealing, when we make probabilistic movies, we introduce correlations between successive samples. So that's what I'm doing with these movies. Yeah?
So the x-coordinate, you're using the numbers from 1 to 6. Can you explain the significance of that?
Okay, up till now, we're just talking about a 6-dimensional distribution, but it looks as if I'm sort of cheating on you, because I could have put those in any order if it was just a 6-dimensional Gaussian, but for it to look like nonlinear regression, these things actually have to have a meaning. So the next question we're going to look at is, okay, how does this work? How do we associate these horizontal coordinates with each other in some way that gives rise to this matrix? So, so let's move on to that. So the question is, where did this 6x6 matrix come from? How are the x-coordinates actually being used in an interesting way so that we end up with something that looks like nonlinear regression? So I've given you a quiz, and the answer to the question, where did this come from, is, well, there is a rule for making the covariance matrix that I'm about to tell you, but a common beginner's question is, well, hang on, why did you choose to make a rule for the covariance matrix? Why not the inverse covariance matrix of the Gaussian? Why didn't you parameterize that instead? And that's what this quiz is about. So, let's see, how are we doing for time? Why don't you have a chat with each other now and work on this quiz? And question 5 is actually the key one that we want to get to. So if you find 1, 2, 3, and 4 at all difficult, please just skip to question 5 and have a look at that. Good. Neil says he can do question 5, so I think that's you should be able to do so. doing it this way. Okay. So, question 5 is a question about 3 random variables, and what we're planning to do with them is maybe predict some of them given some other ones. And here's the question. If we've got a covariance matrix of 3 variables, and if we've got the inverse covariance matrix, is it true that if we just forgot about y3, so this is a question all about omitting a variable, leaving a variable out. If we leave out y3, which we don't care about y3 today, then can we just write down the covariance matrix like this? Is that valid? And question 2, if you take the inverse covariance matrix and say, oh, but we don't care about y3, forget it. Well, I only want to know about the relationship between y1 and y2. Can you then just copy this matrix here? Okay, so that's how I got these candidates. So, hands up, who reckons that A is true? Okay, who's not sure? Okay, so someone who thinks it's true, can you explain why you think it's true and convince the not sure people? Yeah, Ed?
Because you can marginalise out y3 and the sort of consistency of the Gaussians means that you still end up with that.
Okay, we could marginalise it out, or here's another way of putting it. We could just take the definition of a covariance matrix. If we've got a zero mean Gaussian distribution, the definition of one of these entries in here, like this one here, this is the average value of y1 times y2. And if we just say, I don't care about y3, that doesn't affect the average value of y1 times y2. Okay, so that's another way of saying marginalise out y3. The thing that we're actually talking about is just the average of y1 and y2, so it doesn't change. So this is valid. Okay, well, what about this? Who thinks that B is true? Okay, who thinks that B is false? Okay, who's not sure? I've heard some people aren't sure, but good. This is not true. And it's not true just because it doesn't work that way. What the inverse covariance matrix is about is entries in the inverse covariance matrix tell you if you fixed all of the other variables except the 2 that I'm talking about for a particular entry, then what would the correlation between those 2 be? It's not exactly a correlation, but it's an indication of the correlation between those 2 variables if you keep all the others fixed. So the entries in this matrix depend on the definition of all the others. Okay? So if we start saying, oh, actually I don't care about variable y3, I want to throw out some of the variables, forget about them, let's just focus on these guys. That completely changes, potentially, all the entries in this matrix. Okay? So that's why when we do Gaussian processes, we don't say, oh, let's think what our inverse covariance matrix of our Gaussian distribution is going to be. We think about the covariance because what we're actually doing is thinking about a subset of a very large set of variables. Then we do regression, and we've got some data points, and we want some predictions here. We could also ask for predictions here, here, all these different locations, and that would be all sorts of extra y values. And we're saying, oh, well, I didn't actually want those, I just want to predict here. Okay? So, I hope that was helpful, and here's just another couple of pictures to emphasize this distinction. People perhaps get confused about whether covariance matrices and inverse covariance matrices are much the same sort of thing, but they're often not. Here's a situation. Imagine you've got 5 masses connected to each other and subject to Brownian thermal perturbation. So they're in a heat bath, wobbling around, wobble, 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 and they're all connected by springs. What's the probability distribution of their displacements, y1 through y5? Well, you can work it out, and the inverse covariance matrix is to do with who's connected by springs. So each term in the energy here gives you terms in this matrix, describing the couplings between these displacements. So the inverse covariance matrix is very sparse, very simple, tridiagonal, lots of zeros. In contrast, the covariance matrix, all of these displacements are correlated with each other. If this guy goes to the right, it's more likely that all these guys are a little bit to the right as well. So there's positive correlations between absolutely everyone, and this isn't a tridiagonal matrix, and it doesn't have zeros. Okay, so they're very different things from each other, and you should be careful not to confuse them. Okay, so back to the game we were playing. I showed you this. It was just a 6-dimensional Gaussian distribution, but actually I've done something sneaky. It looks like we're doing nonlinear regression. How does it work? Let me now tell you how every entry in this 6x6 matrix was created. First, every one of these points has an x-coordinate associated with it, 1, 2, 3, 4, 5, 6, and I use those x-coordinates to define what the covariance matrix entries are going to be. So the entry at a typical location is, which we'll call col of yn prime, is the sum of two things. First, a covariance function between those two coordinates. And this is in this setup here, it's a decreasing function of the distance between the 2 points. It doesn't have to be, but that's what I was using here. And then the second term is a diagonal term, delta n prime. That's adding on this little 1, 1, 1, this sixth decimal place down the diagonal. Okay? So the second term is just a tiny little bit of extra added noise. The underlying model that we're thinking of here is that x maps to some function which is a function to describe which you would need an infinite number of parameters. So we never actually mentioned those parameters. But we've got that function of x, which is some sort of smooth function of x with properties described by this covariance function, and then a little bit of noise has been added as well. Okay, so the rule to create this matrix depended on 3 numbers and the choice of this whole function. The 3 numbers were the noise level that we put on the diagonal dudes, the length scale that we used to define the distance between 2 points, and this vertical length scale shown in blue, which scales up the entire covariance function. Okay, so that's how I actually chose this matrix, and the result was that we ended up with something that looks like nonlinear regression. So, what's the advantage of this setup? Well, now we can indeed start doing something that looks a lot like nonlinear regression, where instead of only having x coordinates equal to integer numbers, this rule allows us to have arbitrary x coordinates. So up till now, my indices n, which were labeling the columns and rows of the covariance matrix, those are 1, 2, 3, 4, 5, 6, and the x coordinates happen also to be 1, 2, 3, 4, 5, 6. But now we're going to remove that connection. So now the matrix is just a matrix that's going to be n by n, where capital N is the number of coordinates at which I'm interested in function values. And the x coordinates of those different things are going to be called xn. And x1 is no longer going to equal 1, and x2 is no longer going to equal 2. Indeed, it's going to be something like this. Here's, say, 1, 2, 3, 4, 5, 6, 7, 8, 9. And all of these coordinates, you'll notice they're not all of them at integer values, and they're not uniformly spaced anymore either. Right. So, let's go ahead and play with one of those. So we've done 6 dimensions. Now we'll go to a 27-dimensional Gaussian. And here is a movie of samples from that 27-dimensional Gaussian. And what you'll notice is all of these samples look like rather nice smooth curves that you would get from a French curve or a spline or something like that. Okay, so what can we do with this? Well, we can introduce data. So here are 3 almost invisible red blobs, 1, 2, 3. And we can ask, condition on those 3 y-coordinates that we now assume we know, what's the posterior distribution of all the others? And we can answer that question in the usual way, by showing means and error bars at all of the other points. Or we can make a movie, which shows the correlations between these other values. Right. So what we're doing here is we're working with a Gaussian process. This distribution that I've been showing you involved 27 numbers, these vertical coordinates that I've been showing you, but I could have shown you any other vertical coordinate you were interested in. Definition of Gaussian process is a collection of random variables, which are the y-coordinates at whatever point you're interested in. Yeah? And it's a collection of random variables having the property that if you take any finite subset of them, that the joint distribution of those guys is a Gaussian. And that's how we're getting these pretty pictures. So, any questions? Yes?
So you started this section by pointing out that covariance matrices and inverse covariance matrices are different things and ought to be dealt with differently. I didn't quite get why we use a covariance function. Why is it possible to define an inverse covariance function that give entries of k to the minus 1?
Okay, so that's what question 5 was trying to get at, but I didn't do a good job of explaining it. So if there were some rule that I could give you some horizontal coordinates, and I said, okay, these are the points I'm interested in, and I want to describe some curve, and I want to know about its values at these points here. And, oh, maybe I'm interested in these points as well. But we'll come to that in a moment. Okay, tell me what the inverse covariance matrix of these guys is. Oh, I am interested in those after all, sorry. Okay, tell me the inverse covariance matrix. The answer to the question, what is the inverse covariance matrix for these 10 points, depends on whether I'm actually interested in 15 points or 10 points. So I introduce extra points, and it changes the inverse covariance matrix. So there couldn't be a simple rule for saying what the inverse covariance matrix is. Okay, yeah.
So what I didn't understand is why would someone ask you about the inverse covariance matrix?
Well, sometimes inverse covariance matrices are simple things. So in the masses example, which is a way of describing a distribution over functions that tend to be sort of persistent functions. A typical displacement of those masses might look like this or like this. That does actually have a very simple inverse covariance matrix. Another example is splines. If you use splines, the actual inverse covariance matrix associated with splines is very simple. It's another of these sort of tridiagonal or so matrices if you come up with a discrete representation of it. So sometimes it is a convenient representation for very particular models. But if you want a general rule that just says, okay, I'm interested in predicting from these data points at these arbitrary locations, this point and this point and this point and this point, you can't have a simple rule that says what the inverse covariance of those points is. But we can write down a consistent covariance matrix at arbitrary points. Okay, yeah.
I guess the question was maybe more about why would you ask the question, right? The question you're going to ask is, what is the prediction going to be somewhere? And you want the prediction somewhere at some point to be independent of whether you are tomorrow going to ask, an additional question, right? If you have an additional input point, then you don't want the question you ask today to depend on what you might ask tomorrow, right? So the question you're asking is about predictions.
No, actually, the question, you answered my question.
Okay.
Yeah.
that was another good question. I'll answer it for free. Okay, so another question you might ask is, hang on, all of these predictions must depend sensitively on this whole little rigmarole you went through in order to get the matrix that makes all these predictions. So surely you're not suggesting this as a completed solution of how to do machine learning. No, not at all. The predictions do depend on the choice of this function here, and we're going to be hearing a lot more of alternative choices for this function later on today, and it depends on these parameters here. And what I want to show to you now is how the predictions do sensitively depend on those parameters, and how we can nevertheless infer those parameters from data. So let's play around and look at the effect of the hyperparameters. So I'm going to start with the length scale, which is called L, and here there's a little indicator called R because I forgot to change the label. So it's a length scale. If you're from Far East, maybe it won't matter. Okay, what I did in that movie was I took R from a very small value and up to a very large value. And I'm showing you samples from the 27-dimensional Gaussian distribution. When R is very small, you see very, very wiggly functions with very little correlation. This could almost be just white noise here when you have a very short length scale. And in contrast, at very long length scales, let's go back up again. As the length scale gets longer, you see the length scale of typical functions getting longer, and for really long length scales, it almost looks like linear functions with just a little bit of curve to them. So it looks a lot like, these are looking rather like polynomials in which all we've got is maybe the first 3 or 4 terms. Come back down again, and it gets longer again. Okay, so we anticipate that when we make predictions given data, our predictions are going to be hugely sensitive to this parameter L. So here's 3 data points, and here is the posterior distribution. This is the predictive distribution shown in light blue at these other points as I change R. And you see the character of these predictions is changing or what? If R gets really big, then we have these huge extrapolations up there based on just these 3 data points. And if R is really small, then we stop being sure about what's going on in this gap here. And we start thinking, oh, if R is this small, apply this, oh, the function could be way up here, even though there's 2 points coming. Okay? So our predictions are hugely sensitive to this hyperparameter, is the name we give to all of these parameters. Okay. So, can we, nevertheless, even though we're just dealing with 1 point from this Gaussian distribution, the entire function, remember, is just 1 dot in this 27-dimensional space. The question is, can we infer from data what these parameters ought to be? So there's going to be many hyperparameters. Here, in this model, I've got 3. But the idea is, even though we've only got 1 dot that we're trying to pin down, we can nevertheless ask questions like, well, what's a plausible value for the hyperparameter L, given the data I've seen so far? So I observe a few dimensions of this 1 dot, and I can ask the question, what do I infer about the hyperparameters? And the inference, as usual, is done by Bayes' theorem. So we have maybe a prior distribution on these hyperparameters that I'm calling theta. So theta is a generic name for all of these things here. We have a prior on them that might express our initial beliefs about what the length scale of the function is that we're dealing with. And then we've got a likelihood function. We need to know the probability of the data we have seen. The number of points I have seen in my data set is going to be capital N, which here is maybe just 3 or even just 2. So given these small number of observations, we're interested in the posterior distribution of theta. To know that, we need to know how well did theta predict the y values that we have seen. That's Bayes' theorem. So this is the likelihood function it measures how well theta predicted what's happened. And that prediction of y, of that small subset of y, given theta, is just a Gaussian distribution. So it's a very simple quantity. We already saw this equation. So 1 over something to do with the covariance matrix, determinant phi, and a quadratic form with the inverse sitting in it. And that is how well theta predicted y. We're going to look at this now as a function of theta, and to understand what it is as a function of theta, I'm going to visualize this distribution again. So, skipping back, okay, here's what I'm doing now. I'm going to go for the very special case where the number of data points that I've got so far is only 2. Why am I doing that? Well, because in 2 dimensions there's another representation we can make of probability distributions that are Gaussian. Namely, we can show a contour plot of the distribution on y1 and y2. Okay? So we're going back to page 1, where that joint distribution looks like this. And as we vary r, the joint distribution of y1 and y2 changes as shown by these contours. The data is this red dot here. The observation of y1 and y2 tells us that we actually know that this is true. And the question is, how well did those alternative values of the hyperparameter L, how well did they predict this thing that has actually happened? And we can answer that by keeping track of the contours. Let's do that movie again. We're going to start off at very small r, go to large R, and come back down. At the moment, the red dot is just below the orange contour, so we're just under level orange. And as we increase the correlation, we go above the orange contour, and now we're actually way below it, below the yellow contour. So what happened as we went through R, do it one more time. As R increases, the density is going to go up at that point, and then it's going to come down again. Up, 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 down, 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 way down. Okay, and back again. Which is telling us that even if we've only got 2 data points, the likelihood function, as a function of this one parameter L, actually has a peak. So we can plot now how well did those alternative values of R is now L, sorry, L is going to be on the horizontal axis, Yeah. How well did it predict? This is the log of the likelihood, and it's got a peak. So just with a small number of coordinates, we can get information about what L ought to be. And that's what the likelihood itself actually looks like. Not a huge peak, we only have 2 data points, two coordinates measured. But a peak nevertheless. Okay? So here's one of the key ideas. With Gaussian processes, you've got a whole load of hyperparameters that describe what correlations we're expecting, what sort of smoothness properties we have, and those hyperparameters can be inferred from data. Let's do another example. Next up. Just to finish this example, here's 3 data points, and now as we vary R, again, our predictions change in the same sort of way that we saw before. What was happening to the likelihood as a function of that length scale? Answer, here it is, it's got a peak. Okay, so that was moving up to 3 measurements. Okay, next let's do, that's just the most probable value of R, given those 3 data points, which you can see indeed looks sort of reasonable. Next, we'll do A, the vertical length scale, which should be called sigma f. Okay, so again, failure of notation completely get consistent, and we'll do the same trick. We'll say this parameter sigma f, the vertical length scale. Let's look at the likelihood of that parameter. That means how well that parameter predicted y1 having this value and y2 having this value. Let's look at that. So first we'll look at the predictions. Here's the posterior distribution, and you can see as we vary the vertical length scale, the properties of that blue predicted line change. So what was the likelihood doing? Well, here is the red dot, and if you keep track of the contours, you'll see I've taken the vertical length scale way up. I'm going to take it back down again, and notice that it goes up, the likelihood does, and then it goes down. So again, we've got a peak. Okay? So given just 2 coordinate measurements, y1 and y2, we can get a likelihood that's got a peak. And so we can make inferences about that sort of hyperparameter too. Next up, the noise level hyperparameter. Here's now an excitingly large data set of 1, 2, 3, 4, 5, 6 barely visible red blocks. It's all for the movie. Okay, right. So we vary sigma nu. And as we vary sigma nu, our predictions change, as shown by the green and yellow lines. So you get predictions that change with the noise level. Can we infer the noise level? Well, let's look at the likelihood function, and yes, it's got a whopping peak. So given just 6 data points, we can get a good idea within a factor of 10 or so what the noise level probably is, given all our other assumptions that we're making here. Okay. Any questions about what we've done so far? Yeah?
Sorry, me again. Gaussian processes are often described as being non-parametric methods, and you just spent 10 minutes talking about finding the parameters involved. So can you explain a little bit more about what's different between a hyperparameter and a parameter, and whether Gaussian processes are parameterless?
Sure, I'll come to that later on. I've got a slide on it.
Oh, okay.
So we call these hyperparameters because they're playing the same role that hyperparameters play in parametric models. If you want to talk about the parameters of a GP, they've actually got an infinite number, and we're consistently getting the correct answers to models that have an infinite number of parameters without ever having to instantiate. So we're getting a huge saving in FAF. Okay, any more questions? Yeah?
So actually this is from one of your examples that made me think there's an older example. And you're showing each unidimensional thing in this case, but in some of those cases you've shown all that they're unimodal, but in some of those examples presumably would be bimodalities if you look across multiple hyperparameters.
That's right. So the question is, if I showed you the likelihood not just as a function of sigma f, or not just a function of sigma nu, and a third dimension L, what would the likelihood look like? Well, with only a couple of measurements, yeah, it's very unlikely to be unimodal in all of those dimensions. I'm not sure exactly what it looks like. So the likelihood function as a function of lots of hyperparameters can be multimodal, but not desperately so. This isn't a terribly difficult search problem to find those modes, I would claim. I expect we'll hear more about that today if it really is an issue. Experts can correct me. Yes?
Is it ever worth worrying about the width of that peak? Because it seems sort of relatively wide rather than magnitude, I say, rather than just on the maximum.
Yeah, I didn't actually say what I wanted you to do with this function. So you may have been assuming, oh, David obviously means that you should go to the maximum and find the maximum likelihood of hyperparameters. But I didn't say that. That would be a sort of cheap and cheerful, quick and dirty thing to do. And I think it's often a very sensible thing to do. But actually, if we're being proper Bayesians, then we do care about the whole posterior distribution. We should make sure we put that prior in too, and when we're making predictions, we should marginalize over that whole peak. And that's what I would recommend you to do in the quickest and dirtiest way that you're happy with. Okay. Yeah?
While defining the likelihoods with respect to the hyperparameters, you had assumed that the number of points on the curve remain constant.
So the likelihood is defined to be the probability of the data that we have seen, given theta. And so I'm assuming that someone has given me 3 data points. They're asking me to make some predictions as well, but I just need to know what's the probability of the data points that have actually happened. So to answer that question, I only need to know about the Gaussian on the, say, 3 points that have been observed. The fact that I'm going to make predictions at another 100 points doesn't matter.
Okay. So like the likelihoods are independent of whether you consider 100 data points defining your curve or 6.
If you have actually gathered 100 data points, you should include all of those when computing the likelihood and finding the most probable hyperparameters. But if what you're saying is, I've only got 3 points, but I want to predict at another 97, I don't care. The likelihood function doesn't care. All we need to know is what was the Gaussian density on the 3-dimensional space that corresponds to the 3 observations we have actually made. Okay? Good. So, next up, let's just show you some pictures to show that we can do stuff that isn't just one-dimensional. It was convenient to show you one-dimensional pictures where the input space was just one-dimensional, x this way, and 1 output dimension. Now I'm showing you 1 output dimension and 2 input dimensions, because that's the most that we can easily show. And here are 3 samples from 3 different Gaussian processes. The tweak that I've made here is I'm still using the same rule to define the covariance matrix, except that we can have 2 length scales, L1 and L2, for these different dimensions of the input space. And as we go between these different examples, I'm changing what those length scales are. And in the movies, they'll be called R instead of L. Okay, so here's samples from the prior of a GP where the length scales happen to be equal. Next, I'm going to triple one of the length scales. Now you see that it's much stiffer function in this direction. The function values are more constant in this direction, and final movie switches things around. So these length scale parameters can be used to do what we call automatic relevance determination. The idea is if you're not sure whether an input variable might be relevant or not, a completely irrelevant input dimension, something that you should ignore when making predictions, corresponds in this GP setup to a direction in which the length scale is very, very large, which means that the function is essentially constant in that direction. So we can, in a nice, soft, easy way, do automatic relevance determination without having to explicitly consider alternative discrete models, one of which says the variable is relevant, one says it isn't. We've just got a single continuous space to work in. You might worry, what's the cost of doing all these computations? If you want to make predictions at lots of different points, do you have to make a huge, great code variance matrix of all the points where you want predictions in order to get those predictions? If so, let's say if you wanted to predict from these 3 data points at 1,000, would you have to invert 1,000 by 1,000 matrix? Well, it's not that bad. The naive approach, which I used in some of these demos, would have a total cost of n plus n star cubed, where n is the number of training points you've got, and n star is the number of test points, the number of places where you want to make predictions. But you can, by being smart and using the formulae that are in the book on page 16, you can get the cost down to means costing you something just proportional to the number of data points, and error bars on predictions having a cost saying it's n squared per prediction. So we can get the costs down. This is still not low enough if you've got huge data sets. So a lot of what you're going to hear in the rest of this meeting, I think, is going to be about ways to get the cost below the cost of this exact explicit formula. So we'll be interested in approximate methods that get almost the right answer at an even lower cost than this. The sort of things we need to compute, the sort of things you will be hearing about in these...
Sorry, David, just understand, so that's to gather all the pairwise covariances and then go through and generate big...
Okay, if you want predictions at all these n star points complete with correlations, then the simplest way is a brute force computation involving a matrix of this size. If you want just means and error bars on individual predictions, then this is the only cost you need, and here's the magic formula for getting those predictions. If you want correlated predictions, I think finding smart, quick ways that have a cost much lower than this is still an interesting...
But just to understand, this is given as input a lot of the pairwise, your current pairwise covariance function, is it? What's the, what you're computing from initially? What's the...
The covariance function is always an entry, it defines an entry in a covariance matrix, so it is the correlation between y here and y here, just a pair of values. Yeah, that's what you put into this whole process. Right. Okay. So, in talks about efficient methods for doing all this stuff, the sort of things that people need to do in order to make Gaussian process predictions are, if they want predictions, they have to do stuff to do with inverses of matrices. So if we've received data y that is fixed and we want to make predictions a whole load of other places, then we'll have to go and compute a row of a covariance matrix K. These are covariances between the places where we have data and the one place at which we want the prediction, which is now going to run around. And we want to compute this thing for all those points. If we want variances, then as that K changes, which is a property of where we want the predictions, we need a quadratic form of this type. So a lot of the technology of doing stuff with GPs is how can we efficiently do stuff to do with inverting matrices that are n by n, where n might be quite large, 2,000, 10,000, 100,000. If you want to do hyperparameter optimization, if you want to say what's a good setting of these hyperparameters, the sort of things you need to know are either traces of inverses of those covariance matrices, multiplying other matrices of some sort, or perhaps determinants of covariance matrices. The trace is what pops out when you ask for the derivative with respect to a hyperparameter. So you'll be probably hearing about how we can compute those sort of things efficiently as well. How do we choose covariance functions? Well, you're going to be hearing a lot more about that. Let me just illustrate one really simple example of how your beliefs could be turned into a covariance function. Imagine that you really believe the function that underlies the data is a straight line, and you just don't know what the intercept and slope of the straight line is. How do you turn that belief into a covariance function? How do you make a Gaussian process? Well, that's very easy. You say, okay, I believe y is a function plus noise, and the function is m xn plus c. And let's assume that your prior on m and c is something you've thought about, and you've got, Gaussian prior on m with 0 mean, Gaussian prior on c with 0 mean, and you've had to think about that. Now we just ask, okay, what is the correlation between yn and yn prime? And you write it down, here it is, average this under your prior, and you can tell, given your prior, what are your predictions about yn and yn prime? This is all before you look at any data at all. And the answer is, well, there's the noise term as usual, and then the interesting term that depends on the locations of xn and xn prime, the 2 points that we're talking about here when we define the covariance matrix. That's this function of xn and xn prime, namely n squared average xn xn prime plus c squared average. And that is the covariance function that does linear regression. So this is a sort of slightly odd way to do linear regression if you want. It's mathematically equivalent to standard linear regression. Create that covariance matrix and then do the necessary matrix inversions to make your predictions. So here's a whole load of covariance functions you'll probably be hearing about later on today. We've been looking at the one that's called the squared exponential one. You can also, if you had a belief about a function that might look more sort of noisy, a bit more like the footsie or something, then maybe you'd use the Brownian covariance function. If you really liked neural networks and you don't want to lose neural network capabilities, don't worry. You can implement infinite neural networks with one hidden layer with an infinite number of hidden units in them using Gaussian processes. And Chris Williams worked out the covariance functions, and here's some samples from those. Everything I've talked about so far has been regression. We've been talking about Gaussian noise added to a real valued function. What about classification? You're going to hear a lot more about this as well in the next 2 days. And I just want to show you one movie to clarify the connection of what we've been doing with real valued functions with classification. This is one way to connect a real valued function A to a probability which says the probability that we're in class 1 or class 0. We can shove it through 1 over 1 plus e to the minus a of x. And if we define a of x to have a Gaussian process price, so here is a, which is wobbling up and down, just like the pictures we've been seeing before. This is a sample from its prior. Here is what p might look like. This is 0, this is 1. And you see p, once you put it through the sigmoid function, put a through the sigmoid function, p is between 0 and 1, where a was big and positive, p is close to 1, and so forth. Then the generative model can say at each of these x coordinates, where we might have a data point, there is a value of the actual class, which is either 0 or 1. And that's generated in the generative model of things by sampling a single coin toss using event coin with the bias given by p. So here you see a load of 1s shown in blue in the region where 1s are probable. Okay? So there's a movie of that. So now I'll draw samples from the prior. I'm not going to do any inferences, I'm just showing you the generative model. Now, and you see for each A, the classifications of the points can rattle around a little bit, and as A changes, classes are wandering around. So this is a one-dimensional classification problem implemented with a Gaussian process. Okay, there was a question a moment ago about the connection of whether we should call these things parameters or hyperparameters. Let's see what the next slide is and decide whether to come back to that. Oh yeah, okay. So this will be my final thing. So how does this relate to standard neural networks or other parametric models for statistical data modeling? Well, standard stuff is on the left here. You parameterize your model in some way. Your predictions depend on x in a way defined by a whole load of parameters w. That might be all the weights in a neural network. And so you have parameters called w. And in the GP, there aren't any parameters. The parameters, you could think about them if you want, but there's an infinite number of them, and we've sneakily got rid of them. In neural networks, you have an objective function, which is some nasty function of the weights that depends on how well you're fitting the data, ED, and it depends on how big your weights are, EW, if you're using regularization, also known as weight decay. And you have to minimize this objective function. And that's a pain in the neck with neural networks, yeah? You spend a lot of time trying to come up with a good optimizer and worrying about convergence issues and so on. So optimization of M is a pain in the neck. And in Gaussian processes, it's just replaced by matrix algebra, which, at least for small data sets, is a trivial thing. You just write this one line of code, and you're done. So there's a huge saving in fact with GPs, at least conceptually. All the other parameters in the neural network have analogs in the Gaussian process. So you have weight decay parameters if you're sensibly using regularization. And those weight decay parameters are controlling the complexity of your neural network in just the same way as the hyperparameters of the GP control its complexity. And so these three hyperparameters are almost directly equivalent to these hyperparameters of the GP. So the last thing to mention is if you are interested in the quiz questions, on my website, the top link is a 12-page document giving beautiful colour explanations of the answers to those questions. So thanks very much for listening.